A few words about Netiquette. We have over 200 registered attendees today, which means you as the attendees cannot share your audio or video with the rest. But there are other ways how you as participants can interact with the panelists to give their presentation, and that is we have a question and answer section. So if you go to the controls in your WebEx window, you can actually open a Q&A box. And if you have questions about the talks, technical questions at the end of talks, please post your questions as questions in the Q&A box. And then at the end of the talks, the session chair will read out those questions to the panelists, and the questions will be answered by the presenters towards the end of the presentations. What you can also do is you can use the chat function in WebEx to send individual panelists a message. And of course, there are also buttons here. If you like to use them, you can provide visual feedback in the attendee list, like there's an applause icon, etc. If you like, that's not really necessary. But please keep in mind, if you have questions after the scientific presentations, please use the Q&A window where we can then take a look at the questions and answer them for you. There is a time delay between what we do as panelists and what you hear as attendees, which means there may sometimes be quite some time until you hear us talk about the questions which you posted. But please trust us, we'll analyze the questions and ask them in the order they have been received. And then we should be fine with that. After the event, we'll have a recording made available to you. Not all panelists have agreed to be recorded, so it will be only a subset of the presentations you see today. But you'll receive more information about how to receive that recording and how to get into touch with the panelists in a follow-up email after this event as well. And if you would like to obtain the slides which you see today, we'll ask you to please directly contact the presenters and ask for the slides directly from them. The agenda today is pretty much as planned, with one slide adjustment. At 3:30 p.m. this afternoon, there was supposed to be a presentation by Marie-Lise Doublé, who unfortunately cannot attend personally today, but her talk entitled Electrolyte Stability, Reactivity in Magnesium Batteries will be given by her colleague Jean-Sébastien Filol. Many thanks for jumping in on such a short notice. And with that, I'm actually done with the technical so enjoy the conference, and I wish all of us a good event. I'll stop sharing now, and we'll hand over Maximilian Fichtner, who's going to welcome you all officially to the conference. Please go ahead, Max.
Yeah, thank you very much. I would like also to share some slides, if you allow me. Okay. So I hope you can see it. Okay, very good. So yeah, a warm welcome from my side also, and thank you, Christian, for the good introduction, because we, of course, need to get familiar with all these things. Unfortunately, everything seems to be different this time. Rather than enjoying the late summer in Ulm at the Danube and have these very useful chats and conversations among the colleagues, we had to squeeze everything in a few hours only. But I'm nevertheless very happy that we could more or less keep the format that we had in the past and which was so successful. So in that respect, I would also like to thank our colleagues who contributed to this event. Brian Ingram from Argonne will give an introduction in the first talk. And I would particularly like to thank our colleagues from the European project eMagic, who will present their results on the second day. Organizational support, we got from the KIT and the Cluster of Excellence Polis, and everything here is under the umbrella of the so-called CELEST platform. This is the Center for Electrochemical Energy Storage, Ulm and Karlsruhe. So I would like to thank the scientific committee who was particularly helpful in getting the program together. Also, all the speakers today were suggested by the scientific committee, and there was kind of a poll whom to select. So please feel honored if you have been selected. And I also would like to thank the people who will contribute by these 8 invited international talks. We will have 6 invited talks from the eMagic project tomorrow, plus some talks from young scientists of the eMagic project. So there will be some more even tomorrow. And I would like to particularly thank our organizational team around Daniel Messling, Christian Punkt, and Maria Verena Kohnle, who made this event possible and contacted you. The agenda for today we saw already, so we keep the scheme that we have talks about the most important parts of our batteries, so the cathode, the electrolyte, and the anode. And tomorrow there will be again topics in this context by our colleagues from the eMagic project. In the past we have started with many ideas how magnesium batteries can be employed. However, I think that there have been some developments where we have to have an eye on, which might even direct our research. And I just want to bring one example which came up recently. This is a new model from a Chinese company, BYD. This is the model Han. This is the new flagship of BYD. And I find that very interesting because it also may affect our goals that we have on our agenda. This has a new battery, a so-called blade battery, and this is based on lithium iron phosphate. Who had thought? So there's no cobalt, no nickel, no manganese inside, and by which means ever they managed to get 50% less volume than previous LFP batteries, and it even doesn't heat up or burn in a nail penetration test. It has a very good driving range, it's fast and not too expensive. So I think this will be something we have to consider in the future. I think Tesla is coming up with something similar. And then there have been other findings recently in the news. This is something that we don't know whether this is reality or whether this is just a hope. And this is the anode-less solid-state battery, which is seemingly developed by QuantumScape, a company where Volkswagen is now involved with 100 or even 200 million US dollars. And this is supposed to have a driving range 60 or 80, even 80% beyond that of the current battery. So this is something we have to keep in our mind, and we have to ask ourselves whether cars are really the right target for us. Maybe we should keep in mind that we also need very large batteries for stationary applications, and for such large batteries, enormous amounts of materials are needed. And I think these post-lithium technologies that we are targeting at the moment, or let's say several of them, are better suited for such applications. But this is my personal view of things. Okay. The reason behind is just that we have an incredible amount of magnesium resources worldwide. Next week I will be in this region where we see on the left the Dolomites. This is calcium magnesium carbonate, and we have it here even behind the house. Maybe you have it even in your garden. So this is something which we can rely on and which will help us maybe to supply even very large systems. Okay, with that, I'm basically finished. I wish us all a good conference this time, very different from the past. I hope we can continue with our original format in the future. But for today, I thank you all for joining, and I would like to welcome our first speaker, which is Brian Ingram from Argonne National Laboratory. Thank you very much.
Yeah, thank you, Max. Just a brief announcement of 170 participants that have joined us so far, so the audience is already quite full, but not crowded yet. And the first talk of the first session, as Max already said, is given by Brian Ingram from the Argonne National Lab in the United States, and he's going to report on the current status and the quest for high-energy dense magnesium battery oxide cathode in the Joint Center for Energy Storage Research. And I'm going to make him the presenter now, and we are looking forward to your presentation, Brian.
So good morning or afternoon or good evening, everyone. Let's see, get this. There we go. All right. Please let me know, Christian, if this is not showing correctly. I want to thank everybody and specifically Max as well for inviting me, Argonne and J. Caesar, to present at this meeting. Obviously, as was just mentioned, it's a little bit of a weird situation, but I think we're all starting to get a little bit used to this. I even remember to turn off my mute button occasionally. So 2 years ago we did this, and for those of you who can see my screen, a book came out of I think a lot of the discussions. So I've listed my email address on this slide for anybody who wants to reach out and discuss. We can do Zoom or WebEx or conference discussions. I think that this field is still very in need of having discussions amongst those who are involved. And I encourage and I look forward to either seeing you all in person sometime soon or indeed, if need be, on the phone. So today I'll be discussing a little bit about the current status in the quest for a high-energy dense magnesium battery cathode. I will do a little overview as well of the J. Caesar project. So much like Max just mentioned, we are thinking of the wide range of applications that energy storage is needed in, and magnesium batteries specifically. So obviously there's grid storage in vehicles and transportation and flight. And so there's many applications, and finding the right one for the need for the battery is important. So with that being said, J. Caesar, the Joint Center for Energy Storage Research, which is the Department of Energy innovation hub, funds projects at a large scale to answer needed scientific questions. So we are obviously focused on energy storage, and this idea of designing a battery or designing the science to fit the application, as opposed to finding an application that fits the existing science. Sort of on the right side is just sort of a pictorial representation of what we aim to achieve, and that is transformative materials, chemistries, and architectures for targeted energy storage applications, and building those materials from the bottom up. So understanding the key chemistry, the key materials interaction, and designing the materials from the bottom up. There are three primary goals within the J. Caesar program as a whole, and they can be looked at as understanding fundamental description of transport, a discovery science, in how to better design molecules. And then finally, seeing an energy storage concept to the end by building all of this knowledge together. And so the representative areas of science that fit those broad goals are looking at solid and liquid polymer membranes to better understand the solvation of a magnesium or calcium multivalent cation. And you can think from we understand what an idea of solvation is in a liquid, but can we have a unified description of that same cation into a soft material like polymer and into a solid material where you really think of less of a solvation sphere and more of a cage structure, a lattice structure. And of course, that touches on all battery electrochemistry that involves a charged cation motion for operation. Redox MER design is our example area for our discovery science, and this allows for designing molecules that can both undergo redox behavior as well as long-term stability and or self-healing. So we have an effort that tries to understand the science behind better designing of molecules. And finally, the most interest to this group today is building an energy storage concept from the bottom up, and that being multivalent, or more specifically, magnesium ion batteries. So that's obviously the area that I'll be discussing today, the focus of the effort within JCESR on this topic. It's clearly still, I think, an underexplored field, and I think that this conference was great 2 years ago, and I really look forward to hearing all of the talks today and tomorrow as we move forward in this exciting field. Okay, so real briefly, as is already pointed out, magnesium is plentiful and it is inexpensive. So when compared to a lithium-ion system, it's conceptually similar, but does have strong advantages, especially when it comes to volume, density, energy density, and cost. So you can see a comparison of the metals, the charge capacity density, and then also magnesium we know plates better than lithium, and although it's not perfect, and many multiple redox couples do exist. So building on the lithium ion concept, we can move to a more advantageous system, perhaps. Looking at this a little bit more deeply to set the tone for the next 2 days, techno-economic analyses really can sort of quantify the opportunities and define the goals, especially for cathode design. So here we can see the pack-specific energy density as determined by techno-economic modeling versus the pack energy density. And we can see that, we can certainly argue the details, but somewhere in this region is where lithium ion is. And here you can see 3 different categories or classes of cathode materials for magnesium, and you can see roughly where they fall. This stretch here is different states or availability of accessing the charge or the theoretical density of the cathode structure. On the right side, we see a plot which compares the specific capacity of the cathode and then the resulting at the cell level energy density of the system. And you can see that voltage is a very important parameter. In fact, if we look at what would be somewhat arbitrarily, and once again, we can sort of define what transformative energy density is, but if we roughly define it as 750 kilowatt hours per liter, and we define, and we kind of, once again, arbitrarily say what's achievable, and that's based somewhat on reports. This is sort of a probability density of reports in the literature. So we can define achievable specific capacity for the cathode. You can see that really we need to be up into the 3+ volt range versus magnesium metal to see these transformative changes in with magnesium ion. So, setting the stage then for transformative energy density. Obviously, we're going to start with the magnesium metal anode. That's where the benefit really lies. And the choice of cathode defines the theoretical energy density of the cell and ultimately the stack. I showed this plot several times, so many of you may have already seen it, but this is the charge capacity, and this is voltage. Sorry, I don't know why I got cut off there. Of different cathode insertion voltages for different cathodes. The size of the points you see here are proportional to the calculated nudge elastic band calculations of mobility for magnesium. So the larger, the more higher mobility would be expected. So you can see once again, we obviously want to get up to the dense oxide materials to get to the higher energy densities as given by these isoenergetic lines. Okay, obviously an electrolyte, an interface control is required to enable the cathode, and we need a high voltage stability window. We need efficient charge transport, and that's what's represented on the bottom. So J. Caesar attacks both of these challenges, and I'll be talking today about the work we did in the high voltage oxide cathode materials. Justin Connell was speaking at 9:15 Chicago time. I don't know what that is, I forget, in +7 hours in Europe time. And he'll be looking at some of the results and progress that have been made in understanding and describing the electrolytes, especially as it approaches the interfaces. So I know these usually go at the end, but I want to put this up at the front. Almost entirely everything I present today will have been done and worked hard on by someone within our program that isn't me. So I just want to give everybody who was involved, you can see there's a large list of people from multiple institutions that are represented in this particular set of work. And it's a great effort and great program to be part of. So if I forgot anyone's name, if you notice your name is missing and you were involved, or someone else's name, I do completely apologize for that. It was unintentional, but this is the list of people who are very much involved and deserve all the credit. So, what are the critical needs in cathode development? So we know that a cathode won't work if there's no magnesium mobility at all. So you know, diffusion. J. Caesar has spent a significant amount of time understanding the mobility of magnesium cations in the solid state materials for cathodes, and we did a series of theoretical nudge elastic band DFT calculations and looked at a series of different oxide spinels in relationship to changing both cation distribution, so a normal to inverted spinel, as well as compositional changes on the B site. And you can see that inverted spinels have very high mobility, activation energy, low mobility. And as we move towards the normal, that seems to benefit magnesium diffusion through from tetrahedral to tetrahedral site, which is consistent with expectations. And then we can see we can also, by changing the B site cation from manganese to chromium, we can further lower the activation barrier. We then experimentally, using both, this is compiled NMR data taken at variable temperatures, we were able to get activation barriers as a function of temperature, which correspond very, very nicely to the DFT calculations, as well as muon spin relaxation studies. And you can see here, this is on the far right is a comparison of the three techniques, and you can see the very close match between the three techniques. Finally, you can see that the chromite spinel of these three certainly has the lowest activation barrier. So we feel very confident that we've shown that indeed magnesium cations can diffuse at appreciable rates within the spinel oxide structure, and that it should not be the primary limiting mechanism for magnesium energy storage. So as we continue our quest for the high voltage cathode, and we build upon this idea that mobility is sufficient for energy storage needs, we take great care to provide clear and verifiable evidence of reversible magnesium insertion into these structures. And that's done through a series of quantitative, both in situ operando and ex situ characterization techniques that look to understand both all of the either redox activity on transition metal sites, lattice strain with removing and reinserting magnesium, compositional changes to verify that indeed magnesium is present or removed. And finally, in the case of NMR and STEM, we verify even site occupancies and environment of the magnesium. So yes, mobility is not necessarily a barrier, but these systems still remain quite complex in fully understanding, and a level of characterization a high level of characterization is needed well beyond just the electrochemical data to provide evidence, verifiable evidence of reversible magnesium insertion and extraction. So continuing with the chromite, we ran an experiment in a typical coin cell. We ran both a constant current I forget the exact current, and then a constant voltage. You can see about 4.3 volts. What I'm not going to talk a lot about today, but many of you know, this is an extremely challenging condition for electrolytes to survive, and as such, we know that we were oxidizing and decomposing a lot of electrolyte during this process. However, we went ahead and analyzed the resultant material with NMR, and so this is the orange line at the top is the pristine material, and this peak represents magnesium within the tetrahedral site, so NMR being both site and elemental specific. During both the constant charge and the constant voltage, constant current and constant voltage charging, we see this peak shift, but we also see, which is indicative of the chromium redox occurring, but also the volume of the peak decreases dramatically, indicating that the magnesium is no longer found in the tetrahedral sites. There's no evidence of it going into the octahedral sites, and so this is used as data to prove that yes, indeed, the magnesium was extracted from the chromite at these very aggressive conditions. There is only, unfortunately, due to these conditions, the evidence of reinserting magnesium was harder to come by. So we began to do and think about the Spinal structure, which has such a rich chemistry that we can really look at and vary in very trackable ways to better understand the relationship of the magnesium cation with the lattice and the composition of the structure. So using compositional control of these oxides, this is sort of a schematic phase space, as you can see, of different compositions that are considered, and somewhat qualitatively, some descriptions of what we would think, intuitively, what would change if we went along one of these points, compositional lines, like manganese to chromium or manganese to vanadium. They blend, and by doing this, we can blend a number of these theoretical attributes that would be attractive to controlling the Spinel structure as a cathode electrode. So here we can see, for instance, the manganese, which you've already seen this data presented earlier, and now these blue calculations are for the pure vanadium analog. And you can see the vanadium certainly seems to lower the energy barrier quite dramatically. And it should also stabilize, the manganese, however, should stabilize the charge state. So by combining these two materials, there's some the hypothesis is that we can perfect the cathode development. So indeed, we were able to synthesize nanoparticles of the magnesium vanadium oxide Spinel and get single phase material. We can see that we can see the electrochemistry data here on the top right, that it does seem to sustain high capacities upon cycling. We did do this in an ionic liquid, which allowed and supported for the stability of the electrolyte. So we had a little less challenge with the decomposition of the electrolyte in the system. Of course, by going to the ionic liquid, it also forced us to be at generally higher temperatures. You can see that the specific capacity as a function of cycle number, and you can see we started at 110 degrees because of the ionic liquid, and then we actually reduced the temperature to the room temperature. And you can see that although the capacity dropped quite dramatically relative to the higher temperature, we were still able to consistently and over a wide number of cycles maintain about 50 milliamp hours per gram. But as I said earlier, just looking at the electrochemistry data is certainly not enough. So a complete analysis of this material was completed, and to verify reversible magnesium intercalation into the structure. Microanalysis shows that reversible changes in the magnesium vanadium ratio are observed during this process. And then we can also see that reversible XRD peak shifts, as well as reversible shifts in the vanadium oxidation state, were realized. The NMR was done, as I said earlier, we already discussed. And you can see that this peak here does reversibly in the pristine material during the charged material, it goes away and then reappears during the discharge state. It's a little more challenging to see than in the earlier work, just due to the material type and amount that we had, but it certainly is fairly clearly obvious. And finally, we even looked at surface-specific versus the bulk-specific emission spectroscopy results. And once again, you can see, even at the surface, this sort of oxidation shifting of the vanadium that's consistent with the rest of the data, in that the magnesium indeed is reversibly moving in and out of the structure. So we have now the two end members. We have the manganese, we have the vanadium, and then we began to look at solid solution. So here we can see, we looked at both the chromium, which the chromium certainly stabilizes the normal Spinal distribution, and the vanadium tailors lowers the insertion voltage, enabling access to voltages that the electrolytes, current electrolytes can achieve. And we also looked at the chromium-manganese system, once again, chromium stabilizing the normal Spinal distribution, and manganese aiming to promote the magnesium activity as well. So here's some XRD evidence of phase pure analyses, a verification of the solid solution between chromium and vanadium. Yeah, this is the chromium vanadium. No, I'm sorry. This XRD is the chromium manganese evidence, but it's hard to tell from your seat. So if you want to talk further, I'm glad to show more details of this graph. And here you can see NMR analyses of the pristine material. So once again, here's the magnesium peak. It's nice and sharp in the chromite. It's fairly sharp in the manganese state. And you see this broad distribution, which is indicative of a varying environment that the magnesium observes between a mixed manganese and chromium state. The synthetic challenges to obtain these as phase pure materials was overcome, and you can see that we have fairly nice phase pure solid solutions of these materials. So structural and electronic responses to magnesium in these solid solutions is shown to be achieved. And so once again, you can see we can look at the charge state under microscopy and look at the empty tetrahedral sites. We have evidence that magnesium has been removed from the structure. We have lattice strain through XRD showing reversible shifting, pristine charge discharge, and we do see the manganese K-edge reversibly shifting from charge to discharge state. It should be noted that the chromium itself is inactive in this structure. We are not activating the chromium redox center. So there's clear evidence for cubic lattice breathing, as you can see the sort of like charge-discharge strain that we see. And then, as I said, the manganese redox is active, but not the chromium. And so we continue with this. Manganese chromium solid solution, and we compare the calculated voltage profile. We look at a couple of different aspects to this. Inversion is found to be correlated to electrochemical overpotential hysteresis. We did different annealing steps to minimize the percentage of inversion, and we went from we can get from as made 17% down to sub 10% inversion, and we can see so that's post versus the as made, which is the green line. So you can actually see we actually decrease the hysteresis by moving towards the normal Spinal in the structure. Additionally, in using this post-annealed structure that has a lower degree of inversion, where we were able to, this is shown versus a carbon anode, capacitive anode, but we've also done this versus magnesium metal. And you can see that 50 cycles, although there is capacity fade, where we were able to continuously store and release energy with magnesium at approximately 3-ish, or a little less than 3 volts versus magnesium. So, this is quite exciting work, and at the beginning of certainly understanding the relationship of the oxide host structure. So you can see these 3 papers. I'd be glad to share them with anyone. Came out all this year. Obviously, a bit of work that went into them before this year, but they were all published this year. This sort of outlined the progress in the oxide spinels. Of course, the story is far from complete. I've only sort of told you part of the J. Caesar story today. The better understanding of the stability and evolution of the lattice structure, for example, the anti-site defects or inversion, is key. Additionally, surface features are very critical, and we can see that. I didn't go into detail, but between nanoparticles and submicron particles, we can see very dramatic differences that don't seem to be related to the magnesium bulk diffusion. The structural changes at the surface, strain, amorphization, over-magnesiation. And so here's just an example effort of some computed energy barriers, no strain, and then biaxial strain that you might find in a thin film that would isolate surface effects. And you can see that the biaxial strain actually decreases the energy barrier. So for magnesiation versus magnesium extraction. And finally, like I said, the electrolyte stability and efficiency over a wide energy window is probably one of the biggest challenges that this field faces. So I want to thank everybody for their attention. I want to thank the funding from the Joint Center of Energy Storage Research and the Department of Energy, the U.S. Department of Energy, as well as the user facilities that we utilize at Argonne and elsewhere. Thank you very much.
Thanks, Brian, for your fascinating presentation. We have time for maybe 1 or 2 quick questions, and I think Max is going to moderate the questions. Now, there are already 4 questions in the Q&A. Let's see if we get to all of them. If they're quick and if the answers are short, could be fine. And of course, the panelists are invited to also pose questions.
Okay, thank you very much, Brian. Fantastic. So I start with the first one. Bhaskar Akisetti asks, what is the typical density of dense metal oxides, and why spinel structures are preferred instead of layered oxides as cathodes in magnesium ion batteries?
Well, certainly layered oxides have been studied quite a bit and do show evidence of magnesium insertion. One of the challenges we found with layered oxides is because of typically co-insertion with either anions from the electrolyte or water or other various pillared, they can be pillared and their volume can expand quite a bit. And we can't always attribute all of the capacity to simply the magnesium cation. They're very interesting materials and should be continued to be studied. Typical densities of spinels, I mean, the theoretical capacities are often up near around 310 or so milliamp hours per gram of material, and what typical oxides are 4.2 grams per cubic centimeter.
Okay, another question was related to the electrolytes. This is also something I would like to ask. I mean, meanwhile, there should be electrolytes. I know our borate-based electrolyte should be in the order of 4 to 4.5 volts. Have you tried that also?
Oh yeah, that's a great question, and obviously I didn't go into it very deeply today. Yeah, I mean the borate are certainly stable, to at least within a controlled situation. We think that they're great opportunities. What we found is that for some reason there seems to be still some competition against the surface of the oxide structure. And so what we're looking at now is some experiments of understanding maybe a catalytic or surface enhanced oxidation. But no, they work, and we've used them, and we actually get cycling with them. We just see that the cycling rates are lower than in other systems. So it's still not entirely clear, but they certainly seem to be the right pathway to follow.
Okay. Yeah.
Brian, thank you very much. Sorry to interrupt. There are 4 more questions now. I think we have a great opportunity to deal with those because, Brian, you can answer those questions in the Q&A window. Just by typing answers, and you can keep discussing in the Q&A. I'd rather move on time so that we don't run late. I hope you understand. Please engage with the audience, type your answers, and you can keep going on with the discussion. It's not going to disturb anybody. That's the advantage of an online event. And I'd like to thank you again. I would like to announce our next speaker. The next presentation will be Zhengyu Li from KIT, and he's going to speak about cathode design for high-energy, fast kinetic magnesium storage. Zhengyu, the floor is yours.
Yeah, sorry, just have to mute myself, I think, yeah. Thank you, Christian. Can you hear me, first of all?
Yes, we can hear you.
Okay, great. Yeah, thank you, Christian, for your introduction, and also thank Max for your invitation. My name is Zhengyu Li, and I'm from Helmholtz Institute Ulm. So, previously, the previous 2 talks are all about the magnesium cathode, and following their talks, I will also give our recent progress on the development of magnesium cathode. So, a brief introduction to the magnesium batteries. I think most of the points you already know that the rechargeable batteries that utilize in this magnesium anode could have the potential to provide high energy density and could be sustainable and be cost efficient because we are using more and more this abundance materials or elements in this system. And also during the past 2 decades, we have seen a lot of progress in the field of magnesium electrolyte, and actually several successful candidates or let's say successful magnesium electrolyte systems have been built up. For example, this green nut-based APC electrolyte, which is widely used in the community, and this non-nucleophilic electrolyte, which is compatible with the sulfur cathode and also the organic cathodes, and also this chlorine-free magnesium electrolyte with a broad electrochemical window, and this allows us to just to couple the metallic magnesium anode with a high voltage cathode material. So there's no doubt that the electrolyte has been most advanced part in the magnesium battery technology, and in comparison, the cathode development is still in a very early stage, I would say. The fact is that even back in 2000, we already have our first benchmark cathode, the Shepherd phase molybdenum sulfide, as reported by Doron Auerbach's group. But 20 years later, it's still the only benchmark cathode that we are using. So we are still struggling to find a proper cathode which can reversibly insert and deinsert magnesium at room temperature, I would say. And at this stage, the cathode has been a bottleneck issue for realization of a practical magnesium battery. So, as presented previously, there are a lot of issues related to magnesium ion mobility, and the reason is simple: we have a bivalent shuttling ions, the magnesium ions. The fact is that if we want to make use of the high charge density to get a high energy density, we also suffer from the strong interaction between the shuttling ion and the cathode. So this is particularly prominent in case of oxides, where we have this trapping effect of the anion framework, and also this leads to a very sluggish diffusion kinetics. So previously, Seda's group has calculated the ion mobility in some typical oxide materials or oxide host for lithium-ion batteries. And the result is like the migration energy barrier for magnesium is always much higher than that of lithium. And if we look at the value, we see, all of them are actually even much beyond the estimated energy limit of for the ion mobility in nano-sized particles. So with this theoretic prediction, I would see it's not surprising that we normally receive, I mean, in the practical cases, it's we have this slope behavior with fast potential drop in the voltage profile. As this figure has shown by Brian before, and we see that even at elevated temperature, the magnesium storage in spinal oxide is still very limited. And this usually leads to a very small capacity with limited cycle life. So to reduce the migration energy barrier, strategies that needs to be developed in order to weaken the interaction between magnesium ion and the cathode host. And for example, we could just move from oxide to sulfide. I mean, oxide has a relatively high discharge voltage, but I mean, the first step, we could also think about sulfide because sulfur is less polarized than oxygen. And another strategy is, of course, to make an expanded interlayer structure so that we have relatively larger ion diffusion terminals. Also, we could think about reducing the charge density of the shuttling ions by establishing the some novel intercalation chemistries, for example, using the solvated magnesium ion insertion or the magnesium chloride ion as a whole for intercalation. And these three strategies are actually, they are pointing to one direction, that is, we need to have a certain flexibility of the structure so that we could have good enough kinetics for magnesium mobility. But I would say, as Brian pointed out before, that magnesium mobility is not the primary limit or might not be the only limit for magnesium, reversible magnesium storage. And in fact, neutralizing the double charge of the magnesium ion is also not straightforward as we expected. And this is especially if we look at this transition metal compound, if there's one magnesium just come in, we have to change the oxidation state of the transition metal by 2 electrons or by 2. So we need to know that not all the transition metal could afford like the change of the oxidation state by 2. And also, if they have the capability, there will be definitely a drastic change of the ion size and coordination. Here I show you an example of the manganese. So we see that the manganese 2+ has ionic radius, which is 50%, almost 50% larger than the manganese 4+. If we consider both of them are in octahedral coordination environment. And this drastic change will, of course, lead to a deformation of the crystal structure, which is unfavorable for further cycling. So one solution we are thinking is to like share the double charge or even multi-charge over like several atoms, which means we want to activate multi-redox center rather than a single redox center, as in this case. But to do so, we also need to make sure that the redox of these atoms, they are happening at the same voltage. And this means we need a cathode with a delocalized electronic structure. And this has been reported previously, and even in the benchmark cathode, the Schaeffer phase. And if we look at the structure, so the purple bars represent the molybdenum atoms, and we see that 6 atoms are forming hexagonal ring, and they just share 4 electron transfer during magnesium insertion. So on average, each atom only takes about 2/3 of an electron. So that's why in battery performance, it shows a very long-term cycling. And what I want to also point out is that with this delocalized electronic configuration, even the strong magnesium-oxygen interaction can be somehow mitigated. And examples could be like in the polymer cases. So here I show you a polyanthron crenal structure, and basically we have a conjugated structure over the molecular chains, and in this case we could see that the battery could deliver a very nice platinum with very good cyclic stability. So here I show you up to 100 cycles in the publication. And with these 2 points, we are starting to design high performance magnesium cathode. And of course, we will consider both the crystallographic structure and also the electronic configurations. From the structure point of view, I mean the crystal structure point of view, we were studying the 2D layer structure, but to render more flexibility, we have shifted to the molecular chain-like structure. This is kind of quasi one-dimensional structure. And on the other hand, in order to enable this multi-electron transfer, we are thinking to involve anions to this redox process, so that we have this electron cloud over the whole clusters, which could just take the multi-electron transfer. So that's why we choose the vanadium tetrasulfide as a model material and study the magnesium storage capability in this cathode. And the reason is like the atomic energy level of vanadium and sulfur are close to each other. So basically, to prepare the VS4 cathode, we use a hydrothermal approach and have applied the graphene oxide as a substrate to let the VS4 nucleation. And in the SEM image, we see like the needle-like structure, which indicates the quasi-1D structure of these molecules or these materials. And this corresponding EDX spectrum, we have estimated the atomic ratio between sulfur and vanadium, and which is close to 4:1, the stoichiometric ratio of VS4. The XRD pattern also revealed that we have petronite VS4 structure, and the interlayer chain distance is 5.8 Armstrong. So then we have studied the magnesium storage in this VS4 cathode. So this is like a typical discharge and charge voltage profiles. And also we compared with the VS2 cathode, which was also prepared using a similar hydrothermal approach. And this is very clear that we have a much prominent discharge plateaus and a significant increase of this capacity. So the VS4-based cell, we also run it at different current rates, and even at a current of 500 milliampere per gram with moderate capacity retention. In the cycling performance, we see the charge-discharge curves almost overlap after the initial cycle, and this indicates a good reversibility. And also, the cell could deliver a discharge capacity of around 350 milliampere per gram, and this corresponds to like 1.1 magnesium or 2.2 electron transfer. So with this high capacity and also the nice plateaus, we could reach a specific energy of 300 watt-hour per kilo at the material level. So here we also compared the capacity and voltage of our VS4 cathode with other cathode that has reported. And from this figure, we see that VS4 already represents the state-of-the-art cathode for magnesium battery in terms of both specific energy and specific power. And we also learned that further increase in the specific energy is possible if we change the magnesium anode with a cathode anode, because calcium is also like a divalent metal anode, and the respective cell could deliver energy density, specific energy of 500 watt-hour per kilo in a material level, and this is simply because we have a much higher voltage than in case of the magnesium. And also the demonstration of these calcium batteries also indicate that the strategies that we have applied here could also be valid for other divalent ion storage or even multivalent ion storage, so which is quite promising. Then we further studied the magnesium storage mechanism in the VS4 cathode. So basically, we have used this XPS spectrum just to track the change of the oxidation state of vanadium and sulfur. So we have taken the electrode at the pristine state and also at the discharge to 1.3, 0.8, and a fully discharged and fully charged state. So in the sulfur spectrum, we see that during magnesium insertion, we have peak shift from the original state, the red one, to the blue one, or let's say we have new doublet formation during the insertion of magnesium. And this indicates that we have a transformation from disulfide to sulfide. And in the meanwhile, in the vanadium spectrum, we see like a simultaneous change of the vanadium oxidation states to a higher oxidation state. So the peak shift is actually towards a higher binding energy. And other than that, we didn't find any peaks that related to long chain polysulfide or some elemental sulfur or metallic vanadium, which means we don't have this sample conversion reaction taking place during the process. So the question is that why we have the oxidation state change in both vanadium and sulfur, and even the vanadium has been oxidized during magnesium insertion. And this could be explained from the energy diagram of VS4. And we see that here the vanadium's 3D orbitals is penetrating through the sulfur orbitals. With the overlap of these orbitals, we could have some intramolecular electron exchange, so that during magnesium insertion, all the electrons from the out circuit and also from the vanadium has been moved to or jumped to the sulfur 3p orbitals because the new formed sulfur orbitals is lying below the vanadium one. and that's why the vanadium has been oxidized during the process. And with the synergetic cationic and anionic redox, we could achieve theoretically 1.5 magnesium per VS4 structure. And this mechanism is also confirmed by a DFT calculation, where we have seen the charge allocation is mostly on the sulfur dimers. We have also calculated the ion diffusion pathways in this VS4 structure. And here we have considered two scenarios. So the first one is like we assume that the magnesium is just diffusion in the terminals, that is in parallel to this VS4 molecular chains, and this results in a very relatively high energy barrier. In another case, the magnesium could also jump from one disulfur or sulfur dimers to the next. So in this case, we have a much reduced energy barrier compared to the first cases. So this result is quite interesting, and also it reminds us of the ion hopping in polymer. If we look at the structure, we see that VS4 is also kind of like a polymer structure. It has a molecular chain structure, and that's why it might also have the same hopping mechanism as in the polymer cases. But in case of the polymer, because of its even much more flexible than the VS4 structure, then this also allows us to have this even interchain hopping, or even with ion cluster hopping together with some anions or some clusters. So this is quite interesting. So to sum up, I would say that first of all, we have proposed to consider the local charge balancing during magnesium insertion. And in this regard, we believe that multi-electron redox might fit better to the multivalent ion storage. And this could also be a design principle for magnesium cathode or even other multivalent cathodes. And as we presented before, the cathode with delocalized electronic structure will be more interesting and more promising for ion mobility. And we know that the delocalized electronic structure could be easily achieved in the organic cases, where we always it's easy to have this conjugated structure. But in case of inorganic material, we have to think of to engineer the band structure of the material so that we have some overlap of the orbitals between the cations and anions, and this might be a solution for a more dense structure compared to the organic cases. At last, we also learned from the polymer that the 1D molecular chain structure might render more structural flexibility, so that the battery system or the ion mobility will benefit from this structure. So this could be also something we need to consider when we design or further design a magnesium cathode. So at last, I would like to thank or acknowledge the financial support from Polis, from the eMagic, and also the Maximal, and also the colleagues and partners that contribute to this work and giving me firmly support. And with that, I would like to thank you all for your attention.
Thank you very much for your talk.
Thank you.
Thank you for staying so nicely on time. We have plenty of time for questions. So to the audience, maybe you have joined later, if you have a question, please post your question in the question and answer section. There's an option. If you go to the WebEx controls, your conference window, you can open the question and answer section, and please post your questions to Zhenyu there. If you're on the panel and you have a question, you may also unmute your microphone and just ask your question directly. Max, I hand over to you.
Okay, thank you very much, Chen Yu. I have two questions at the moment here coming in from Abraham. The charge capacity for VS4 is larger in all cycles, question mark. Why? How can cell capacity be retained with this large irreversibility? Reminds me a little bit to the case that we have in lithium-sulfur batteries, for example. So how this is possible?
Yes, this is actually a good question. We are, as we have presented in the publication, but I didn't show you here, is we always have a relatively low Coulombic efficiency, or we have more charge than a discharge. So the reason could be, on the other hand, we also find that theoretically we could achieve 1.5 magnesium insertion, and in the real case, this only corresponds to around 1 or 1-to-1 magnesium insertion. So that's why I'm also wondering whether we have make full use of the cathode materials here. So the overcharge here showing in the charge discharge plateau, I was thinking maybe from some side reaction of the cathode. For example, when we have the breakdown of the sulfur-sulfur bonds, and this might not be completely or 100% reversible, so that we are losing some kind of the capacity, and also this will somehow lead to some maybe there will be small amount of magnesium sulfide formation, which is just detached from the structure. And as you mentioned, Max, it's in case of the lithium-sulfur or magnesium-sulfur cases, we have this overcharge. So it might be similar at that one also.
Yeah, of course, it's probably a different mechanism. There's another question from Gregorio Ortiz. Nice work. I think you avoid at any moment the presence of oxygen, right? The mechanism of reaction is interesting. Could you explain why the OCV of the cell is 1 volt, and why is it so different to the 2.4 volts as theoretically expected?
2.4 volts. I don't understand why we have 2.4 volts from theoretic calculation. But basically this 1 volt, so the initial discharge was, we believe that it's coming from the magnesium anode side. This is also the case in the magnesium sulfur case, and in other insertion cases we have studied. We always have some activation cycle in the beginning. That's why we have some voltage drop or voltage which is lower than the rest of the cycles. So I think it's mostly contribute from the magnesium side.
Okay.
I have a question here, which was, I think, asked to the host only, so probably only I see it, from Samuel Bertolini. He wrote, nice presentation. In the VS4 cathode, have you observed any extraction of sulfur from the structure in the presence of magnesium ions or not?
No. So we did the XPS, and we didn't see any elemental sulfur formation, or at least in what we have analyzed. So maybe further analysis is also necessary to check much more into detail how it works, because for me personally, I also think it's not completely reversible, and there must be some side reactions happening. Yeah.
Yeah, I think the question was rather whether maybe magnesium sulfide has formed. But if this is very small, you won't see it in an XRD, right? And it would also not appear as such in the XPS.
Yes, this is difficult to see, because in the XPS we cannot distinguish the vanadium to sulfur bond and magnesium to sulfur bond. So this is the problem.
Yeah. So this might be a potential degradation mechanism.
Yeah.
Okay.
There's another question here. Maybe just a quick announcement to the audience. It is better if you post your questions in a way that you address them to the whole panel and not just to the host, because I'm the host and I'm doing all sorts of things. I don't want to ask the questions. But there's one more here, which I can do now, from Sai Gautam Krishnan. Nice talk, Zhenyu. A 1.5 EV barrier is actually pretty high, way higher for a sulfide system, exclamation mark. Did you calculate this with DFT? If so, do you have any idea of how magnesium intercalation can occur at the high rates that you mentioned?
This is a good question, actually. I think this is mainly because we have considered the magnesium to sulfur bond during the ion diffusion. So that's why we have a higher diffusion energy calculated here.
Okay.
Or have they been obtained differently?
Sorry, I didn't.
Are these DFT results or?
Yes.
Yeah.
These are DFT.
Okay.
Yeah, because I mean this is kind of a controversy, because you have here barriers up to 2 volt, 2 eV, and and if you compare it to the spinels, this is much lower. And nevertheless, it seems that the magnesium is migrating well in these chain-like structures. Yeah, so it may be the way how you calculated it, or how it was calculated from the colleagues at the DTU, right? Or who did it? Yeah. Okay. So, do we have more questions? I don't see any.
There's one more here at the bottom.
There's one more. Do you have it from Jacob Hartler-Jacobsen? Do you have an estimate on the particle size that was used and the cathode loading?
The particle size, as I showed here, there's a SEM image. Just a moment. So I would say it's a nanometer or nano-sized particles. And the loading of the active material is 70% of the active material and 20% of carbon and 10% of the binder. Yeah.
Maybe the question about loading was also referring to how many milligrams per square centimeter on the cathode?
Oh, yeah, exactly. Sorry. Yeah. The loading is like around 0.821 milligram per square meter.
Square centimeter. Yeah. Okay, thank you. Well, thank you. Then move on. I don't see any additional questions. Thank you very much, Zhenyu, for your exciting talk.
Thank you.
Great results. And then we'll move to the last speaker of the first session from today, who is Jean-Sébastien Filot. He is substituting for his colleague Marie-Lise Doublé, who cannot attend today. So thank you very much for jumping in on such short notice. And we're looking forward to your talk and how to provide stability and reactivity in magnesium batteries. The floor is yours.
Okay, thank you very much for the invitation first. And I want also to say that my colleague Marie-Lise Doublé is very sad not to being able to assist to this very nice meeting. So now I'm going to switch to some kind of story. And if you have any questions, don't hesitate to contact me through my email. First, I'm a theoretician of interface electrochemistry, and as any interface electrochemistry is quite complex because you have to both compute the active materials, the double layer, and the electrolyte. And because of that, there's a lot of complexity, and one of the main complexities that is appearing in this kind of interfaces is the presence of surface charge and very strong electric fields that are going to change completely the chemistry of the system. So of course, this kind of interface are very important because they are directly part of degradation, STI processes. For safety, they are directly linked with dendritic growth. And of course, for all the batteries characteristics such as power and efficiency, they are directly linked with the electrochemical kinetics and catalysis that can occur at this point. So they are very important really to understand. And theory is really the tools to look at, to have a look at this position. So first, there are many existing models to really try to understand what is happening on the electrochemical interface. The first one is, of course, you can use extract from the Nernst equations, where mostly, if you do that, as the Nernst equation is done for uncharged system, we model system with interface with no charge. It's mostly what was developed for electrocatalysis by Noskov. But these things can work very well, but sometimes it can bring some issue. As an example, I'm going to talk about the simplest system, that is the lithium reduction and formation of nanocrystallites. As you see the shape of the nanocrystallites, if you compare them to what you get if you only use the surface energy you get from DFT calculation, you get very, very different structure. So you see that the classical approach that is using zero charge can be very wrong to getting proper energetics for the interfaces. So what you need is to get into more complex modeling that should include the surface charge, of course, electric field, and eventually explicit and implicit solvation of your interface. In this case, you get some kind of equivalent Nernst equation that will depend on the local electric field. That is not practical. So to be practical, we are using the free electrochemical energy. That will be our main energetics. And it works both for add some molecule on the surface, but also molecule in the double layer. So it allows investigating a wide range of very different behavior in electrochemistry and answer both questions and reactions happening on the surface or really in the double layer. This approach, what are we doing? Mostly we are computing a charged surface. Of course, if we are going to compute the uncharged surface, that is mostly the statistical approximation, but we are going to get other charge system. We are going to charge the surface, and we are going to have more and more, for example, oxidized system that will get different potentials that we are going to compute, and we can also get the reduced system. From this simple approach, we get the free electrochemical energy that is present there, and that is mostly an inverted parabola shape. With at the bottom of it, you will get the potential of the zero charge, and the curvature of it will be proportional to the surface capacitance. Then we already get some very specifics of surface and interface electrochemistry. So if I redo that for the last time to lithium, what I get is, if I look to the uncharged system, in fact, I get that the uncharged system for lithium is associated with a potential of plus 1.4 volt relatively to lithium. So in fact, when you are modeling uncharged lithium surface, you are modeling unstable system, because at 1.4 volts, the stable form of lithium is not metal lithium, it would be lithium plus. So you are computing a system that is not possibly experimental. So to get to really negatively charged system going to zero relatively to lithium, we can get a charged system, and we find that we get completely different surface. When it's uncharged, it's a 1-0-0 surface that dominates energetics, and when it's under reduction, under negative potential, it's a 1-1-0 surface. And in this case, you see that we are able to reproduce the shape of lithium particle. So it's one thing to say that charged surfaces are really important to really get proper surface and interface energetics. So next, in my little tutorial, how do we model electrochemical reactions at an interface? In fact, we need a redox pair. We have some kinds that will be react as the oxidant, for example, some kind of Ali plus over the surface. And we will need another interface that will compute, that will be the reduced interface, that will be, in this case, for example, lithium, that will be deposited on the surface. And in this case, when we have computed that, we can extract the electrochemical reaction. When the two free energy curves just cross, we get the equilibrium potential associated with the redox system. We get the redox equation, and we can even get the number of exchange electrons. In this case, that will be close to 1. Not exactly 1, because it's also including the surface polarization that is needed to maintain the potential constant. So below this potential, the reduced lithium metal will be the stable form, and above it will be the lithium plus. So by using this formalism, we are able to investigate the electrochemical reaction on the surfaces or in the double layers. So now I will switch back to magnesium. As the previous speaker just said about, it's really an interesting material to get some better batteries, but many problems are still to solve. And one of the many problems that were already talked about is the solvent problem and the stability of the solvent at the interface. So we spent some time investigating what is happening with magnesium in this case. So first, we checked that we get the proper energetic for magnesium. So we model the magnesium nanoparticles at different potential. We find that if you do the uncharged surfaces, we get a very long potential relatively to magnesium, plus 1.6. So it will be, once again, a metastable system. The structure corresponding to the zero charge will be quite similar. It will be mostly an bulky octahedra. And when you go to very high over potential, you get some kind of hexagonal packlets that are system in correspondence what is found experimentally. So things seems to be fine also for magnesium as for lithium. Now, the first step of our study was investigating the simplest reaction, that was the transformation of magnesium 2+ into magnesium metal at the interface. We did a study on the different solicitation spheres, so we find some kind of always octahedra over the magnesium. We did it for two solvents. The classical one used in the classical carbonates used for lithium that we modeled in this thing that is of course not the best for magnesium, and we are able to get the reduction potential in ethylene carbonate. That will be minus 2.37 versus standard hydrogen electrode. That is very close from the experimental data that is around minus 2.4. If we look at the same reaction, we of course exchange two electrons, and we can also do that with another solvent that will be DME. And with DME, in fact, we get mostly the same thermodynamic properties for the reduction of the magnesium 2 under magnesium 0, that would be also around minus 2.4. So for the moment, everything seems okay. But when we did all this array of experiments, we had some kind of surprise. When we go under too much reductions, we get some kind of instability into both systems. When we go beyond about minus 0.7 relatively to the equilibrium potential, there's a spontaneous reorganization of the solvated cation. that was not observed in previous studies with lithium. So it's really something specific to magnesium in this case. And what we did observe is different behavior depending on the solvent. For DME, we observe a spontaneous decomposition into ethylene and mostly methanolate, that's the magnesium dimethanolate at this potential. So mostly that would correspond to reduction not of the magnesium 2, but of the solvent around. And for ethylene carbonate, we also observe spontaneous evolution, that is this time a dimerization. We have two ethylene carbonate molecules that will just form a carbon-carbon bond with many other reorganization in the geometry of the ring. So in this case, we observe that with these different solvents, we have very different chemistries. Could of course be somehow expected. Now, we wanted really to identify the associated process, this time not associated with the reduction of the magnesium, but with the reduction of the solvent molecule that is associated, coordinated to the magnesium atom. And in this case, we look for, to start with the molecule in ethylene carbonate, and what we find that we find a specific free energy for the new dimer. And then we just try to find the behavior of this dimer under this type of oxidation. And what we get to around 0 volts, we get simply the reaction going back to the initial state. So we have some kind of reversibility between two ethylene carbonate coordinated and some kind of dimer. We get, of course, all the potential, the thermodynamic process. We get that the reduction just occurs there, meaning at plus 0.7 versus magnesium, also meaning that the ethylene carbonate is reduced before the magnesium. That can be a problem. And this also occurs for the DME molecule, but this time with fragmentation. And of course, the fragmentation is irreversible. When the fragmentation occurs, there's no turning back because the ethylene molecule cannot find its way back to reform the initial DNA. And this also is associated not with the reduction of the magnesium, but a reduction of the DME molecules. So we can already define a stability domain where the solvent is going to be stable, but we have another new domain where the solvents will be only metastable. We can find it, but it's not the most stable species. The one will be either the dimer or the decomposed DME molecules. And anyway, above a limit, there's no stability at all of the undimerized or unfragmented solvent. They will just become unstable. So there's a stability limit for these systems. So exactly, how can we understand this instability? Actually, this instability is really specific to the solvents that are coordinated to magnesium. If we do this study with simply ethylene carbonate or DME at the interface, we observe no dimerization, no spontaneous decomposition. You really need to have magnesium that coordinates the solvent. So what is happening? So mostly in the case of free solvent, not coordinated to the magnesium, just in the electrolyte, the Fermi level just is in the electrode potential range. The Fermi level of the surface is sitting just between the HOMO and the LUMO of the solvent molecule. So in fact, no electron transfer is possible. There's no reduction that can occur. But when we just coordinate the solvent molecule to magnesium, the effect of magnesium on these molecular orbitals is to shift down all these orbitals. And in particular, the LUMO is going to be shifted down, and it can be shifted down upon the range of reduction of the surface. So because of the attachment to magnesium, some of the attached solvent molecules are going to be reduced and can undergo this reduction that will lead to either dimerization or fragmentation. So one of the problems of the magnesium 2+ is really created some kind of activation of the solvent molecule. It's very close to what is observed in organic chemistry, and it's some kind of electrophilic activation that facilitates the solvent molecules reductions. That, in fact, is really the problem. Solvent alone is stable, but when it's coordinated to magnesium, it becomes sensitive to reduction. Okay, so can we go a bit further on? And we know that we have some metastability, but we want to get more precise, more detailed range of this metastability, because we know that for many solvents, even in their metastability range, it can be used in electrochemistry. In this case, what we looked at is the total charge of our complex with the magnesium and the attached solvent around it. Is first the Russell shell, and with that we are going to look at the charge as a function of the potential. What we see is we really get a +2 charge most of the time, and at some point, electron is transferred to the surface toward the solvated Mg2+, and some reduction occurs. And this can give us a first hint where the electrochemistry is going to happen. So it allows to give us the electrochemical inactive magnesium 2+, and when electrons start to be transferred, starting to activate the solvent reduction, it gives us the activate reduction, where certainly all the dimerization and fragmentation are going to happen quite fast. So because of that, you see that the blue line is the potential of reduction of magnesium. What we observe is we still have a very small zone, about 100 millivolts, where we can get an electrochemically inactive magnesium in DME. But this electrochemically inactive DME will start to go quickly in the reduced activate zone. So we are going to reduce both magnesium and the solvent. For ethylene carbonate, it's about the same, but ethylene carbonate should be quite better. The electroinactive zone is slightly larger around magnesium, so ethylene carbonate should be better. But of course, ethylene carbonate is not better, so there's something more to understand. And to really understand, we need to focus on where the reduction just occurred. This can be given by the Fukui function. The Fukui function is some kind of mathematical tool, but that gives you the chemical ID of reduction center. When we compute it, it gives us where the electron flow from the electrode. So when I just add electron to this molecule, I directly see that in the DME case, I'm getting some kind of sigma star system reduction that will lead to CO bond breaking and the formation, you see it there, of some kind of C double bond, and that tells you that going to the formation of ethylene and methanol. While for the ethylene carbonate, what's going to happen is a reduction of the pi star bonds. And we also see that we are going to weaken a lot, because we are going to into an interbonding space, the CO bond in the ring. So that means in this case, we are going to favor the dimerization, but we are going also to favor the ring opening in ethylene carbonate. And when we look more closely at the reduction process for DME, we directly see ethylene formation and methanol. And once we get this species, the problem is it cannot be reduced anymore. The methanol presence, when we compute the reduction potential versus magnesium, is very low. So that means we are creating a mostly inactive material. So the consequence of the solvent reduction in this case is the creation of inactive material, and from the form that's certainly going to precipitate at the electron. In the second case, in the case of ethylene carbonate, we form the dimer, but what we see is a strong ring opening tendency. And when ethylene carbonates undergo ring openings, it tends to form a polymer. So the problem with ethylene carbonate, it should be a better solvent, but the problem is going to initiate a polymerization reaction at the electrode. That is not a very good idea because it's going to certainly passivate the electrodes. So if we look at the experimental results, I've said there's a magnesium reduction. And what we see, if we look at the zone where our solvents that is coordinated to magnesium start to be unstable, we see that some kind of reduction already happens. That is certainly a mixture of magnesium to reduction, but also of DME, and some kind of precipitation that is going to isolate the electrode, and we see that there's a decrease of the intensity recycling. In the reduction part, we also see that the amount of oxidized magnesium is quite low in comparison to the one that was formed, and we have very low efficiency, meaning that there's some kind of secondary reaction that is happening. In the case of ethylene carbonates, what we observe is, in this case, if I set over there the magnesium 2 plus magnesium reduction process, at the potential where the solvent ethylene carbonate is starting to get reduced, we see some kind of decrease in the intensity that probably is linked with the formation of the polymer that start to form and start to passivate the whole electrode and decreasing quickly the intensity to very low values. In the second part, what is interesting also with ethylene carbonate is actually we find a peak at around minus 1.4 that directly corresponds to the dimer-monomer equilibrium we previously find. So that's certainly one other indirect proof that things are happening with this kind of magnesium. So to summarize this part, mostly what is annoying is DME is not stable enough under reduction and just will break down. And ethylene carbonate could be stable, but the problem is undergoes strong activation and you go to do polymerization and you are passivating your whole electrode by creating something polymer. So a good question is, how can we prevent that? One proposition was adding chloride to your electrolyte and to form different kind of magnesium chloride compounds that we compute. But the problem to really investigate your reactivity, you really need to understand the relation between potential and chlorination. So mostly what we need to do is to do a Courbet diagram for this kind of system. So we did it, and mostly we just find the experimental observation with all the different magnesium chloride compounds, more or less complex, that are formed. So we are happy, mostly we can find experiments, but the problem actually is that's the bulk electrolyte diagram. But bulk electrolyte diagram is not really interesting to understand the electrochemistry. Because, in fact, what you need is what is happening on the surface. So we need to really build the surface Courbet diagram. And in this case, we see that the Courbet diagram is really changed because of the very strong electric field at the interface. And in this case, the active species at the interface are not the one of the bulk. And then once we have reached to this kind, we can look at the stability of the species. Of course, with pure magnesium, we have observed we have a very low metastability of the DME. It starts to be reduced quite close to the limit of reduction of magnesium 2. But if we use some chloride compounds, the metastability range is strongly increased. And the more we add, the more it is increased. So chloride is certainly a very good thing to improve the electrolyte stability by, in fact, decreasing the electrophilicity of magnesium. But of course, if you add too much chloride, you are going to precipitate MgCl2 and you are going to clog your electrodes. So to conclude, here is just the explanation that is Mg2Cl2. And when you look to Mg2Cl2, in fact, Mg2Cl2, you don't undergo any reduction on the DME molecules. So it's really the proof that the chloride has a protective behavior with this kind of system. So to summarize everything, with our approach, we can go to thermodynamic parameters. I've not shown it there, but we can also get kinetic parameters and link with electronic properties. And we can have also ideas on why magnesium is such a pain with the solvent, because it's a strong Lewis acid and it's activating the reduction of it. It's also activating the oxidation of it. In some case, I'm changing the chemistry, but I won't talk about that. So thank you very much for your attention, and I'm ready for any questions.
Thank you very much for this very detailed analysis and for sharing it with us. We have 5 minutes for questions. Max, do you take over?
Yes, yeah, thank you from my side. This is on the one hand surprising, and it's very, very interesting. I mean, we of course suspect the highly charge or the high charge density of the magnesium, that it does something, but yeah, that it can really lead to decomposition. This is a bit new to me, actually. Do you know whether there is more evidence for this decomposition mechanism? Like, did somebody observe the ethylene that you propose?
For ethylene carbonates, there are some experimental observation of really thick layers of it that were analyzed mostly to be organic. So some kind of ethylene carbonates polymer is coherent with what was observed. And it certainly really the polymerization of ethylene carbonate with magnesium that doesn't occur with lithium is certainly one of the problems of all the solvents that have ring carbonates. So
okay.
And for the DME, there are some observation of ethylene production upon cycling. So
really?
Of course, the problem with the interface, it's very difficult to really have things that are happening mostly 1 nanometers away from your electrodes.
Mm-hmm. If I take that for granted, this mechanism, then this would mean that we would observe more and more ethylene when we get higher and higher magnesium concentrations in the electrolyte, right?
Actually, yes. The problem would be that you are going to precipitate the magnesium OCH32 that's going to decrease your surface area. So you have some kind of something that looks like flat potential. So you have passivation and creation at the same time. So theoretically, yes, it will depend on the precipitation kinetics.
Okay, I see. I don't see more questions at the moment. So if this is the case, I thank you very much for these new insights. I think this is very important. Please say hello to Marie-Lise and send her our best regards. And with that, I think we have reached the first break of this meeting, right, Christian?
That's right, exactly. So maybe to finish up this first session, all the panelists of the first session can briefly turn on their cameras again. Thank you very much for your contributions. We'll now take a 15 minutes break and continue at 4:15 Central European summertime. The panel will now go behind the curtain into the practice session and check out if the upcoming talks will work. And I'll start an automatic presentation for the break. And as I said, the panel will meet in the back in a moment. So thanks for participating. We'll be back 1:15. Bye-bye.
Thank you.
Okay, does that look good? Can you hear me?
Yes, all is good. I gave you a thumbs up.
All right, perfect. All right, yeah, thank you for the introduction, and thanks a lot for the invitation to speak today. So, as was mentioned, I'm Justin Connell, a material scientist at Argonne National Lab, and today I'm going to talk about some recent work that we've done looking at anion effects on electrochemical response in magnesium and zinc and copper electrolytes. And as all the speakers, up to now have summarized, there's a lot of opportunity in these systems, and we've really learned a lot over the last several years of looking at these multivalent systems. I'll sort of highlight a few highlights relevant to what I'm going to speak about today. The first of which being there's some really strong evidence that as we move to reductive potentials, the formation of any kind of monovalent species in these electrolytes can lead to some interesting chemistries, in particular parasitic reactions that lead to decomposition of the anionic species in your electrolytes. In addition to this, it's been shown that species that are present at very low concentrations, even ppm levels, can have a really outsized impact on reversibility. And so we need to pay attention to not only the majority species in the electrolyte, but also things that may be present even at minority concentrations. And finally, as the last speaker pointed out very nicely, the addition of chloride to a lot of electrolytes can really significantly alter solvation structure and magnesium surface chemistry, in a lot of cases leading to improvements in coulombic efficiency. Now, with all this insight, there's still a lot of questions we'd like to know. In particular, there's been a lot of theoretical evidence that monovalent ions form, but thus far we haven't really been able to show experimentally that they're actually present. And so we'd like to know, do these monovalent ions form and contribute to parasitic electrochemistry and resulting in lower efficiency? In addition, we'd really like to know, what's the specific role of chloride in promoting reversibility in these systems? And most importantly, can we replicate it in other electrolyte species so that we can enable compatibility with high voltage cathodes? Because obviously chloride is incompatible with high voltage oxides. And then finally, beyond how oxophilic magnesium metal is, are there other fundamental differences or similarities between magnesium and other divalent metals that drive differences in apparent reversibility? And really where we'd like to go with this work is to understand, can we develop common descriptors between divalent cations in order to better understand their behavior in different electrolytes and really start to develop predictive understanding of what kind of response we can understand, and importantly, how we use that to develop new electrolytes. So the approach that we're taking in this work is to move away from looking at just sort of bulk plating and stripping response and move towards dilute solutions of the working divalent cations. And we do this in order to access both mass transport and diffusion limited conditions for metal deposition and start to evaluate more mechanistics of the processes themselves. And I've thrown copper into the mix in the study specifically because you have an experimentally accessible 2+1+ redox couple. So we can start to get some idea of, what does the electrochemical response of the 2+1+ redox event actually look like in these non-aqueous multivalent electrolytes. The other advantage of going to dilute solution is we can use the rotating disk and rotating ring disk electrodes methods to look at again, more mechanistic information about the impact of solution speciation on the response. Because we're working with dilute concentrations of our working cations, we need a supporting electrolyte, and in this case, we're going to use a lithium-based electrolyte with TFSI and diglime. TFSI we choose specifically because even though the magnesium chloride and chlorides in general are fairly poorly soluble in these ether electrolytes, in the presence of TFSI, you can actually have significant amounts of chloride to modify electrolyte speciation. The electrolyte itself gives us a wide electrochemical window. Magnesium and copper are very far apart in terms of redox potentials. And the other benefit of using a lithium-based electrolyte is we can use a lithium metal reference electrode to get a uniform referencing scheme between all of our different working cations. And then finally, I'm going to be using a glassy carbon working electrode in all cases. And the reason for this is because it allows us to rule out a lot of other surface-specific effects like EPD, surface-specific anion absorption, and really lets us get at sort of the fundamental deposition stripping response. And just to show sort of what the background chemistry looks like in this electrolyte, you see, we have more or less featureless electrochemical response across the whole window of the different working cations we want to look at. Although we do see the onset of reduction current at about 0.9 volts versus lithium. which matches with some predictions from DFT results that I'll discuss in a little bit. And so we do attribute this indeed to TFSI reduction. But what this means is that there's definitely going to be some background current when we're depositing magnesium, which should initiate about 200 millivolts below this. That does complicate the analysis a little bit. You can see that a bit in what comes. But just to give you a sort of brief outline of what I'm going to talk about, I'm first going to describe the effect of chloride on improving reversibility in TFSI-based electrolytes. And we found basically a very interesting cooperative effect between TFSI and chloride that yields the overall improvements in reversibility in this system. And then I'm going to sort of generalize this effect and show that it's not only active in the zinc-based systems I'm going to discuss, but also appears for magnesium and copper-based systems. And not only that, extends beyond chloride to other mixed anion systems. So to summarize sort of the benefit of going away from more dilute, more concentrated electrolytes to more dilute systems is summarized here, where in this voltammogram of a 0.2 molar zinc electrolyte with a 1-to-1 ratio of TFSI to chloride, the only reason you see a peak in this voltammogram is because the potential is reversed after you initiate zinc deposition. And so it just, as you reverse the sweep, you see a peak in the maximum current, and then you obviously see a peak because you deposited a fixed amount of metal. When you go to a more dilute system, you actually access mass transport limited conditions. And the reason you now start seeing peaks is because of that mass transport limitation. And what this shows is that sitting underneath of these sort of individual peaks in the bulk plating and stripping is additional complexity. And specifically, if we compare the response of this mixed TFSI chloride electrolyte to a TFSI only electrolyte, you see that what's actually happened here is there's an additional redox couple that's present upon the addition of chloride relative to the TFSI only electrolyte. And so because we're working at in dilute conditions, again, we can utilize rotating disc and ring disc electrode techniques. And just as a brief refresher for those who may not be super familiar with these techniques, the idea of an RDE measurement is you have a cylindrical electrode that's embedded in an insulating collet. And if you induce rotation of this electrode, you can force convection of your reactants to the surface of the electrode and essentially set up a constant delivery of your active material to the electrode surface. And the result of this is that instead of seeing peaks in this mass transport limited case, you actually start to see plateaus corresponding to a diffusion limited delivery of your active species to the electrode surface. And what this lets you do via the Kurecki-Levitt equation, if you vary the rotation rate, you can actually extract kinetic and thermodynamic process parameters related to the process that you're studying. Rotating ring disc it relies on basically the same setup, but with the addition of a ring electrode to the outside of your working disc electrode. And what that allows you to do is sort of generation collection experiments, where as you generate or consume the species of the disc electrode, you can monitor perturbations to the current on the ring electrode as you generate or consume that species of the disc electrode. In this case, we'd be consuming as we consume zinc or whatever species for metal deposition. You would see a decrease in the steady state current at your ring electrode. So the really interesting thing is that as we start rotating in these mixed TFSI chloride electrodes, we see two diffusion limited plateaus in the voltammetry. And this second diffusion limited plateau occurs after zinc plating initiates. And what we see is that what appears to be the case is that there are two separate nucleation overpotential events as you go to more and more negative potentials corresponding to two separate initiations of zinc deposition. What we also see is that both of these reduction plateaus exhibit Levitch type behavior. So they exhibit a linear increase in the limiting current density as you go to higher and higher rotation rates. And so this suggests that definitely multiple species are active in the system. But to confirm that they are indeed related to zinc deposition, this is where the ring disc technique comes in very handy, where as we drive constant zinc deposition on the ring electrode by holding the potential at 2.1 volts, so corresponding to this first reduction plateau where we know zinc metal deposition is taking place, we see that as we go to more and more negative potentials, you see a decrease in the ring current corresponding to consumption of zinc by the disc electrode. And we see both two distinct decreases in that current density decrease, indicating that both of these reduction events are related to the consumption of zinc at the disc electrode. I won't show it here, but if we do a corresponding experiment where we hold the ring electrode at very positive potentials, we don't see any evidence of reoxidation of a solution species such as a monovalent zinc ion. So we don't really see any evidence of zinc plus formation. So what the voltammetry tells us is that there are multiple solution species that are leading to the deposition of zinc metal in this system. And so to understand what's driving this, this behavior, we can start playing around with the solution composition. And so what I'm showing here in this scan is focusing only on the reverse scan. So where deposition ceases, more or less corresponding to the thermodynamic potential for metal deposition. As we play around with the chloride concentration, we see two very interesting things happening. The first of which is as we increase the chloride concentration, the magnitude of the current density associated with this first reduction plateau decreases, suggesting that in order to access the full current density accessible in the system, you have to go to more and more, or higher and higher overpotentials, more and more negative potentials. Correspondingly, as we increase the chloride concentration, though, we see the onset of metal dissolution shift to lower overpotential, or more negative potentials. And so what this suggests is a cooperative effect between TFSI and chloride that's resulting in the overall more reversible electrochemistry in this system. And to illustrate what I mean by that, we can return to this idea of there being essentially two overlaid redox couples, where if we highlight the TFSI-based contribution to the voltammetry, we see the early onset of metal deposition, but a higher overpotential for metal dissolution. And why we believe the deposition is able to initiate earlier is due to the relatively weaker association strength of TFSI with the zinc cation. And so it essentially takes less energy to desolvate zinc from a TFSI-rich coordination relative to chloride. We look now at the chloride-based concentration contribution to the voltammetry. We see, again, metal deposition initiating at higher overpotential, but the dissolution initiating at lower overpotential. And this can be rationalized by the fact that the chloride relative to TFSI is more strongly associating, and so there's essentially more free energy released by reassociating a zinc ion, a cation with a chloride ion in solution. So there's a higher driving force to resolvate zinc into a chloride-rich speciation rather than a TFSI-rich. And so if we then sum the contributions, this is what leads to the overall more reversible voltammetry that we see in the bulk plating and stripping behavior. And you really wouldn't have been able to rationalize this if you hadn't gone to the dilute case and been able to pick out the individual contributions of the ions. Now that said, this is at this point a little bit speculation based just on voltammetry. And so to determine whether this effect is reasonable, we turn to density functional theory to investigate some potential active species that might be leading to this behavior. And so what we did is simulated a variety of different zinc coordinations with varying numbers of TFSI, chloride, and diglime, TFSI, chloride anions, and diglime solvent molecules in the first solvation shell. And basically, in order to down select, we rule out any complexes that were either unstable to one electron reduction or that yielded reduction potentials outside of the window where we see any evidence of zinc metal deposition in our voltammetry. And what we find is several stable complexes, and I'll highlight a couple of them here. One set of complexes which are chloride-rich, where we either have zinc solvated by a diglime and a single chloride anion, or zinc solvated by a chloride anion and a TFSI anion. They both give relatively similar reduction potentials. What we also see is several stable TFSI-rich coordinations, with one TFSI and one diglime, or with two TFSI anions, both again giving fairly similar reduction potentials. And what we see is that the trend predicted by DFT matches very nicely with what we see in the experimental results, where the TFSI-rich coordinations predict reduction onset positive of that with the chloride-rich coordinations. Not only that, these structures actually match very well with the experimentally observed thermodynamic reduction potentials that we see in the voltammetry. And so what this says is that this idea of this cooperative effect between TFSI and chloride leading to the overall more reversible electrochemistry does appear, in fact, to be a reasonable hypothesis. So while this cooperative effect is exciting, the next question obviously is how far does this effect extend? Can we bring this to other systems? And of course, there's a magnesium ion conference, so of course I have to talk about magnesium. And so we wanted to see, first, does this effect extend to other working cations? And what we see is that indeed, if we add chloride to a TFSI-based electrolyte, we see more or less identical behavior for copper, zinc, and magnesium. We see the appearance of additional redox features upon the addition of chloride, both for copper and magnesium, that look very similar to what we see in the zinc systems. We'd also like to know, again, I made the point at the beginning of my talk, can we mimic what chloride is doing? Does this effect extend to other anions? And so to understand what trends we might expect, we turn again to DFT, and we see that as we start to play around with anions of differing association strengths, we do see a consistent trend of a shift in the redox potentials. We move to more strongly associating anions like chloride to very weakly associating anions like PF6. And we expect very similar trends for both zinc and magnesium. So we want to know, to what extent can anion association strength really be used to tune the reversibility of metal plating and stripping? And so we begin by exploring a sort of chemically similar anion to TFSI, this triplet anion shown here schematically on the bottom left. And what we see is that for both zinc and magnesium, we see very similar behavior for both the mixed TFSI chloride and triplet chloride systems, where the magnesium more or less looks identical, where we see 2 oxidation features and 2 reduction features in direct analogy to what we saw with the zinc system. But very interesting for the zinc triplet system, while we again see 2 distinct reduction events, we only see 1 obvious oxidation feature. And so what this seems to suggest is that the addition of triplet, the combination of triplet and chloride shifts this second dissolution event to a potential very similar to that of chloride. And so the question here is, can triplet be used to mimic chloride? Can we start to move away from chloride in these electrolytes to improve the versatility of these systems? And so if we compared the plating and stripping of just the 2 constituent electrolytes, so TFSI only in the black and triplet only in the blue, we see that the whole redox event appears to shift to lower overpotential, consistent with the higher association strength of the triplet anion. And so, to answer this question, can triplet be used to mimic chloride? We see the answer is actually yes. Where in direct analogy to the mixed TFSI chloride system, we see 2 distinct oxidation features in the mixed TFSI triplet system. And if we overlay the voltammograms I just showed, we see that this first oxidation event overlaps exactly with that of the TFSI only system. But this lower overpotential peak sits directly in between the 2, the triplet only and the TFSI, suggesting that there is mixed TFSI triplet coordination in the system, in some contrast to what appeared to be distinct populations in the TFSI chloride system. We also see that only 1 obvious reduction wave, which is again consistent with mixed coordination driving deposition, and the location of this peak is again directly intermediate to the triplet and only in TFSI only cases. Now, this isn't just relevant to the dilute case. If we could look at now a bulk electrolyte, a 0.2 molar zinc electrolyte with the TFSI or triplet only, and then the mixed TFSI triplet system, we see essentially the exact same trend, where we see improvement in reversibility relative to both electrolytes and the onset of oxidation, again, sitting intermediate to where we see for the TFSI only and triplet only cases. And so we very strong evidence that this cooperative anion effect appears to be active for both the TFSI chloride and the TFSI triplet systems. So we return back to the predictions of DFT and we start to compare anions of differing association strength. We see, what I've already shown to now, the TFSI chloride and TFSI triplet case, we see the additional oxidation event to lower overpotential relative to the TFSI only. If we move to more weakly associating anions, though, very interestingly, we see the location of this additional oxidation event shift to higher overpotential in direct analogy to what we see and what's predicted by the DFT. And interestingly, in the case of PF6, we also see the onset of reduction start to creep more positive of that with the TFSI only system, which is, again, consistent with this idea, because with a more weakly coordinating PF6, it should be even more easier. It should be more easy to desolvate zinc cation, desolvate cations relative to TFSI. And again, as we saw before in the TFSI triplet case, all of these mixed anion electrolytes, it results in improvements in reversibility relative to the TFSI only case. Again, in keeping with the predictions of DFT, where we see improvements in reversibility of greater than 200 millivolts for all the mixed anion electrolytes we studied. And so what this tells us is that anion association strength can really serve as a descriptor for reversibility of metal deposition. And more importantly, it suggests a new set of design rules for electrolyte development. These systems that we chose here certainly aren't optimized. There's a long way to go between what we have with these triplet and PF6 relative to what chloride can do, but we're moving in the right direction. And it suggests that we can really start to think differently about how we design electrolytes, where we don't have to get everything from one anion. We can start to design independently what's guiding one half reaction versus the other. So to conclude, it's shown that divalent metal deposition can really involve the complex interplay between the different anions present, highlighting specifically the TFSI chloride system, where the overpotentials for the deposition and stripping half reactions can really be controlled independently based on the specific anions. and via their cooperation results in lower overpotentials for plating and stripping and improvements in solvent efficiency. We've shown that anion association strength can serve as a common descriptor for reversibility of multivalent anodes, where this effect appears to be active for all of the anions and divalent cations that we studied in this work. And again, as I mentioned, this suggests a new set of design rules that we can use to develop new electrolytes. And the one comment that I'll leave with is that what these results seem to suggest is that interfacial speciation likely differs significantly from that we see in bulk measurements of electrolyte composition, as even these very weakly associating anions like TFSI and PF6 in particular appear to participate very strongly in both the plating and stripping reactions. And so even though these species appear to form solvent-separated ion pairs in the bulk electrolyte, clearly they begin to associate it more tightly with the cation as they approach the electrified interface. So we have to think more about that as we move forward in our understanding of these electrolyte systems. So with that, I just want to acknowledge everyone else who contributed to this work and the facilities at Argonne as well, and obviously the funding from the Joint Center for Energy Storage Research. And so with that, I'm happy to take any questions.
Thank you very much, Justin. We have time for a discussion. So in case you just joined recently, if you're a regular attendee, you can post your questions on the Q&A section, a special question and answer window, where you can submit a question in writing. Please address your questions to the panel. If you are a panelist and you would like to ask a question, just unmute yourself and speak up, and Max is going to take your questions and read them out when you post them.
Yeah, thank you very much, Justin. Very nice and also very valuable, I think. I mean, we all had the chloride in mind when it comes to improving the reversibility, but chloride is corrosive, and if you can substitute that by a different anion like TFSI, this is of course actually a new field that you open here. Yeah. I see two questions at the moment. One is from Samuel Bertolini. Nice presentation. One question about the calculations.
I think that was for the previous talk. That was to Jean-Sébastien.
I'm sorry.
And it was already answered by Jean-Sébastien. I think we have no questions on the Q&A at the moment.
That's correct, yeah. I'm sorry, I just saw them.
Oh, there is one. There is one now.
There's one now. What about the solvent effect on bidionate?
Yeah, that's a really interesting question. So, especially thinking as we go to more, weakly associating anions, thinking about, carborane or the borates or oxyaluminates, at some point anions are going to become too weakly associating, and the solvent is probably going to start to take over. And so, yeah, or just playing around with solvent chemistry. I mean, here we focused only on diglyme, but as we move, from the different length of chain glymes or other solvents completely, yeah, I imagine that the solvent will also at some point start to participate in these reactions. So it probably represents also a sort of a third knob to turn here, second knob.
Mm-hmm. Okay. So did you use this effect already to really build cells and cycle these cells, and then you find differences, or?
So far, no. I mean, we're still sort of the early days of tuning this chemistry. I mean, the specific anions I chose even are just basically what I could buy on Sigma. Or, we had some great collaborators who were able to synthesize a couple of these salts, custom for us. And even with that, but I don't get into it here, but impurities in the electrolyte also really dominate. The point I made at the very beginning of my talk. I mean, water obviously is a big problem here, but other residual impurities from the synthesis, residual halides, residual other cations, all these things play in. And so there's sort of two things that have to be tuned here. One is obviously this anion association effect, but also the purity of the salts has to be really tightly controlled. And so getting salts of varying enough chemistry and also high enough purity is something else we really have to pay attention to here. And so that's something we're actively working on, obviously, but in terms of going to full cells, it's getting a salt that's pure enough to really you'd be certain that you're not doing some other parasitic chemistry is definitely a big challenge.
I think purity is something which is really disturbing us sometimes, because you find some strange effects, but this is not due to our main compound, because this is just some spurious things that come up by some ingredients. Okay, thank you again. I don't see more questions here, so then I would like to move on to the next speaker. Thank you, Justin.
Thank you.
Thanks a lot, ladies and gentlemen. Many thanks for the invitation for this talk, and to also have maybe a little bit a broader perspective on this issue, and coming more from an environmental perspective and doing an LCA for magnesium sulfur batteries. And actually, why are doing all these investigations towards post-lithium batteries? Because well, the present lithium-ion batteries can be considered as unsustainable. Why? Because the production costs and the life cycle costs, which include also the use phase, are still too high in many applications. The environmental impacts and the social impacts of the production are quite high, and that includes also toxicity of the materials, which is also already mentioned several times during these talks. The technical performance needs improvement, especially to decrease the costs and the environmental impacts. On that, especially focus then on the use phase, and that means we have to improve the cycle lifetime, the internal resistance, maybe the calendric lifetime, and so on. And the present recycling of lithium-ion batteries is too complex, and you need a lot of energy to get all the materials outside. And in fact, lithium, for instance, it's quite often not recycled because the costs are too high to get the lithium outside. Also, if some recycler always promise it's technical possible to get the lithium outside, but the costs are in most cases too high to get the lithium outside. And they only recycle in the moment the really expensive metals like cobalt, nickel, copper, and so on. Then also safety issues are problematic of lithium-ion batteries, especially during the use phase, but also the second use phase are more and more important. If batteries from maybe mobile application in vehicles then are used in a second life for stationary application, there are safety issues which has to be solved. And last but not least, also for the recycling, is the safety issue a big problem because of the electrolyte, which is flammable and explosive, and so that's always a challenge. Always a challenge for the recycling process. Yeah, and last but not least, the basic idea is, of course, to replace critical metals like cobalt, lithium, nickel, copper, and so on. And if you look on the criticality map of the EU, which was several years established, then you see in red from the EU perspective critical metals or raw materials, and in blue the not so critical metals and raw materials. And in fact, we did some investigations regarding lithium-ion batteries and the availability of these materials in the long term. That means if we would use such materials until 2050 for really a revolution or transformation of the mobility sector, or the transformation of the energy sector, which also needs then, or there's then a high requirement of stationary storage facilities. So, and the outcome of all these investigations, and you can find the publications on our website from my group, the outcome is that there are really not only cobalt is critical, it's also lithium, it's also copper, it's also nickel. That means also NMC 811 is maybe not the solution to have a not critical or not to solve the criticality of the raw materials. So, and now, but the magnesium batteries, and if you look for now for the criticality of magnesium, now it's really above everything. So from a EU perspective, magnesium are one of the most critical raw materials, and that's really a little bit astonishing, especially, and that's also mentioned several times already. It's magnesium is the 8th most abundant element on the Earth's crust. And the resources, and that's dolomite, magnesit, samsonite, a lot of magnesium evaporites, brines, even seawater, and then all the resources are really enormous. And so there is not really, well, a big shortage, and the availability should be not a big issue. But the problem is that magnesium is predominantly produced in China. So they take over the market more or less. Yeah, there's only minor production in Russia, Kazakhstan, and a little bit in US and South America. So yeah, that's a basic issue. And but on the other side, magnesium is very important for the EU, especially for alloy production. And the EU is also only depending on imports. Yeah? And also, if there's a small recycling established in the EU, but net, we are totally importers, and that makes this material so critical. And there are only small activities in the moment in the EU, in Turkey and Serbia, and of course, that's not in the moment, the solution of this problem. But what happens? Why is China now leading that? Well, they really offered in the past magnesium to really low price, and it was so low that the smelters in EU was not competitive. So they shut down the last one in Norway and France, and so until today there's no magnesium production in EU besides the small activities, as I said, in Turkey and Serbia. So the criticality, and that means that the EU perspective is not based on the availability of the magnesium, but it's rather on the high dependency from imports, especially from China. And so that means from a broader perspective, yeah, well, if one magnesium batteries would be successful and there's really foreseeable that magnesium, there could be a certain industrial production of that, then of course there should be then a magnesium metal production also established in EU in time. That's the point. Yeah. So yeah, be prepared for if the magnesium batteries will be successful in the future. But now coming to this to our investigation and the investigated prototype cell. That was a cell which was produced by Custom Cells in Germany and consists of one anode, two cathodes, sulfur cathodes, and then in a pouch housing. And this prototype is of course not optimized. There was only the idea that there should be a cell with a function. And so the casing, that means the pouch casing, was just totally too big. The separator was double. It was a folded separator, and therefore there was also too much electrolyte in the cell. Therefore, we considered actually in our investigations 3 different scenarios for such investigation. That was the magnesium sulfur baseline scenario. That means really the prototype not optimized as it is. And then to optimize this cell regarding the pouch mass, because the pouch mass was totally too huge, and we reduced the pouch mass from 45 weight% to 3 weight%. On 3 weight% actually represents the normal weight percentage in a normal lithium-ion cell. With the next evolution, then just theoretically, that the magnesium evolution 2, Then to reduce the separator share, that means from 10% towards 2% of the separator, and reduce the amount of the electrolyte accordingly. These are the three scenarios which we investigated in this environmental investigation. Because the cell, from our perspective, of course, it's quite important, but we need a battery, and so we consider then the magnesium battery, which consists of 80% cell in our scenario, 5.5% of battery management system, and 40.5% of casing. That's the normal numbers, average numbers, which you can find for lithium-ion battery systems. So we just use this as a comparable system. For our life cycle assessment, as I said, it's a prospective life cycle assessment because the magnesium battery is really still in the early stage of development. That means it's not a hard LCA with really hard results. So that's always there's an outcome of the results, and then maybe receive new information from the technology developers, and then we improve our LCA. So that's always a snapshot, a certain snapshot for this investigation, and the results are normally used from the technology developers to improve their systems, to make their systems more sustainable or environmental friendly, for instance, just get rid of some toxic materials. But that's the considered system for this life cycle assessment, and I will not go in detail what is a life cycle assessment, because that would be maybe too much for this presentation. So if you have questions regarding life cycle assessment, especially for energy storage, so please contact me after this session. So and you see now here the system boundaries. We have some inputs and outputs, and in general, well, the inputs are always energy and materials, that's the raw materials, and energies in different forms. The output are beside the product, the magnesium-sulfur battery, and also emissions to the different areas to water, soil, and air. And you see within the system boundaries the different components of the cell. That's the anode, the cathode, the electrolyte, and I have to say the electrolyte are still a normal electrolyte. It's not such a sophisticated electrolyte what we already heard today with boron and so on. That would be the next step, to have also really a modern electrolyte. And then with all these components, then you have the cell assembly with all the different components. And last but not least, then for the magnesium battery, then to add the battery management system, the casing, and then to have in the end the battery of the magnesium cell. So that's the system boundaries. And with the next slide, we see already the result of this study. And as I said, there are preliminary results. And that's here we showed a really simple environmental indicator. That's the cumulative energy demand, CED, and that counts all the different energy forms which are used for the production of the cell in this case. And that means not only the energy, for instance, electric energy, which goes in this system, but also then maybe the coal, which is used or to produce the electric energy. That means the complete pre-chain of the energy provision. And if you look for this not optimized baseline scenario that we have for this cell type, that we have a certain different contribution to the overall impact. And you can easily identify that natural gas has a certain contribution. The natural gas is used for the production of the cell, the provision of heat for the production of the cell. Then electric energy for production is the biggest contribution. The housing, that means in this case the pouch of the cell. Also electrolyte really has a big contribution, and also the magnesium itself. So, and if you compare now this scenario, this baseline scenario now with this two other scenarios which I showed beforehand. You see that the impacts with the theoretical scenarios are significantly lower, and you can see that very significantly that, for instance, the housing, which has a big contribution in the not optimized case, has now really a little impact, and it's more reliable, I would say. And even now with the next evolution, then with the separator, which is now adjusted to normal values, although that looks now more reasonable, and also now with the saved electrolyte. So that could be the direction of the improvement of such a cell, also if it's just on a theoretical level. Now to other impact category, it's called global warming potential, GWP. That's the CO2 impact and the equivalents also from other gases. And you see here actually more or less and very similar results. The not optimized magnesium battery cell has quite a big impact with this first optimization of the adjustment of the pouch. Now absolutely better, and now even with the improvement regarding the separator and the electrolyte, now it's really a relatively low value. And what means relatively low value? Just for the comparison, I put here now the LFP battery system, and you see, at least from the feeling, that now with this theoretical improvement of the cell, that we at least in the range of this LFP system. But I have to say, for this LFP data set, that's already quite old. That means it's from 2011. That means present LFP systems, maybe now even now the new one from BYD or Tesla, that could be significantly lower. So that would be quite interesting. But at least you see, if you improve the cell in a certain way and do it more in to a cell which are comparable to lithium-ion battery cell, then you are in a certain way competitive, and that's already quite good. To see where in detail where the differences from the impact. So now we did also some sensitivity analysis, and though it's quite important to know where's actually the electricity production for my battery production, and of course there could be maybe coal power, for instance, like in Poland, or nuclear power or renewables, and so we try to consider that and looked for the energy mix of the electricity provision for 3 different countries, which are maybe stand for a certain type of electricity mix. Switzerland with a low CO2 impact because they have a high share in hydro and renewables, and only a little share in fossils for the energy provision. In contrast, maybe then the EU in the middle, more or less, with a noteworthy fossil contribution, then maybe China, which has still a major contribution from fossils, especially from coal power plants. So that are the 3 different countries for the potential production of the batteries. And here now you can see already then the influence of this electric energy provision. And for the EU, it's the normal, that's maybe in the middle between China and Switzerland, because it has also from the CO2 emissions are in the middle. And the biggest impact from China and the lowest impact from Switzerland. And so maybe you can easily understand why companies like Tesla or Northvolt in Sweden, they are so interested to have a green pre-chain for the electricity provision. That's quite important, that the impact of the cell production is really quite low, and to be competitive with other technologies. So that's the reason why they're doing that. Well, in this investigation, we did not include the use phase, like cycle life, calendric life, the internal resistance, the efficiency of the cell, or power density, and so on. And that is, of course, the next step, but the uncertainties are still quite high, and there are not so much cells available, which are really full cells and are tested regarding the cycle stability or regarding internal resistance. So if you have a project, or if you have a cell in your lab, please contact us. That would be quite interesting for us to see where's the range, where can be such magnesium cells perform. And another point which is not included is, of course, recycling. I say the recycling of lithium-ion batteries is quite difficult. It costs a lot of energy or chemicals. And so there should be different, for all the post-lithium batteries. And with the next graph, or maybe I can stress this a little bit. If you see now here the different value in the cells, from NMC 111, there's a lot of cobalt in it, and therefore the value is quite high. So if you recycle such a battery, then you are quite lucky because you can get all the cobalt out of it, and also, of course, other materials like copper and nickel and manganese. But already with NMC 811, that's already not so nice from a recycling perspective, because the cobalt is only a low amount of cobalt is in such a cell. And when with LFP, there's no cobalt. And then, of course, from a recycling perspective, it's not so interesting, especially the black mass. Maybe then the aluminum is interesting and the housing, but not the black mass. And if you think about the magnesium-sulfur system, the value is even lower. And then, of course, then you have to think about how you can recycle such a system with such low value of the materials. And from our perspective, then, of course, there's no way to go a really complex recycling route. There's only the way after the use of such a battery, stationary or mobile application, or maybe after second use, then to bring it to a mechanical treatment and then try to have a direct recycling of the cell. That, of course, would be beneficial. Otherwise, the costs for other processes are too high, and you would lose a lot of money. And that's, of course, not in the kind of thinking of circular economy. So that's maybe just some reference regarding our ongoing work. It was, the first LCA was already published for magnesium batteries in 2019 in this nice book from Max Fichtner regarding magnesium batteries. Then we had some publications regarding recycling of different battery types, and last but not least, just accepted in energy storage. The assessment of a new generation of magnesium-sulfur battery systems. That's from my side. Thank you for your kind attention. I'm looking forward for the question. Thank you.
Thank you, Marcel, for this interesting perspective on things. It's good to see that maybe there are also other aspects to consider, right? We always say, well, magnesium is so abundant, no problem, but there are other aspects which also need to be included in the picture. So I think there's at least one comment. Max, I'm handing over to you.
In fact, there is a comment from Daniel Höche that general information on primary magnesium production can be found, for example, here in Zuliani, Douglas, and Douglas Reason, making magnesium a more cost and environmentally competitive option from 2012. So
good. I look on this specific source. Thanks a lot.
Okay. I have a question, and on your slide 9, you had the energy costs for the production of a watt hour, so the watt hour per watt hour.
Yeah.
So you came to a number of 1600 watt hours for 1 watt-hour of a system. Can you compare that to lithium-ion battery? I mean, we had the comparison with the global warming potential, yeah, and we were at least in the range of a LFP battery from 2011, yeah. But how is it here? I mean, 1,600 watt-hours per watt-hour.
Yeah,
this is a lot.
Yeah. Yeah. Well, actually, well, if I delete now this one, and you see with this improvement, yeah, then you are already in a nice range, yeah, between 800 and 300 or 400, I can say. Yeah, so that's already quite nice. And actually, it is. I have the slide not with me, but it's really similar to this GWP, global warming potential. It's very similar. We are in the range with this improvement, but this is only a theoretical improvement. So the technology developers, they have to show that they can produce such a cell. So therefore, I'm quite interested that maybe other groups, or maybe, of course, also the groups that are in Celeste, that they develop such cells and test it, and yeah, that we have primary data, and then if we receive more data, then of course our results are more reliable. So I'm looking forward. So that means that in the moment a theoretical improvement, and we need some confirmation from the technology side if this is really manageable. But I think it's manageable, but nevertheless there needs proof of that.
Okay. I think there will be more of these studies when we make more progress with our materials.
Yeah.
Yeah. So I think that the first pouch cells have been made already with systems that work kind of well. Yeah. Among them are organic materials, few inorganic materials. So let's see how the whole field develops.
Yeah.
So at this point, I would like to thank you. I would like to thank all the speakers today for their great contributions. We saw a lot of new results, and there were really interesting achievements in them. So how can we get better recycling? How can we boost the mobility, etc.? And I'm now looking forward to the day tomorrow, yeah, where the eMagic project, where I would say the senior scientists and the young scientists are going to present their results in 12 talks tomorrow, and this will be moderated by the coordinators of this project. So with that, I'm finished. Thank you all. I hand over to Christian.
Yeah, thank you very much, Max. I don't have much to add. Tomorrow we'll continue at 2 p.m. Central European Summer Time. Of course, all panelists are asked to join early, 20 minutes before, so that we can iron out last issues. And as Max said, Luis and Alberto from CELITEC will host tomorrow's session, and I'm looking forward to it, and I wish you all a pleasant afternoon. Special thanks to the colleagues from Japan and China and Korea who have really stayed until now. It's now late at night, so thanks for bearing with us, and we'll see you guys tomorrow. Thank you very much.
Yeah. Bye-bye.
Bye.